Greetings. I'm Joe French, coming to you from my classroom in Mount Pleasant, Utah, and this is topic 2.4, connecting differentiability and continuity, determining when derivatives do and do not exist, and we'll go over some examples. So first of all, what does differentiability mean? Well, a function is differentiable at a point if the derivative exists at that point. So basically, if you can take a derivative, the function is differentiable. And our derivative, just to remind you, is defined as the limit of the difference quotient, the slope, as 2 points come together on a function, and is interpreted as the slope of the line tangent to a graph at a point on the curve. So what does that mean? It means that if the derivative exists, the limit of the difference quotient exists because they're the same thing. The difference quotient can't exist without points to calculate from. So these calculation points must converge to the point where the tangent line connects to the curve. So our limit is equal to the value. If the limit of these points is equal to the value of the point, then we have a continuous situation. So therefore, differentiability implies continuity. But the flip side of that, continuity doesn't necessarily imply differentiability, which means we can have continuous functions that aren't differentiable. Now, how might that be possible? Let's look at some situations. First of all, let's look at a quick reminder of what functions look like if they're not continuous. We have functions with a hole in the graph, and those are removable discontinuities. Here's another one with a hole in the graph over here, the third example, but we have a new point down here at the bottom, and that is also a removable discontinuity. Then we have these other two functions where the graph behaves a little differently. The second graph, where our graph increases without bounds on either side of 0. And if a graph increases or decreases without bounds, we call that an infinite discontinuity. Our graph is going off into infinity. And then we have this graph that looks like a bunch of steps or a stairway. And there we have jump discontinuities, where our graph is approaching one value and all of a sudden we find ourselves at another value as we continue to move from left to right or right to left. So if any of these situations occurs in our function, our graph is not differentiable. We can't take a derivative at that discontinuity. No derivatives at discontinuities. At discontinuities. You can't draw a tangent line if there's no point, at that place. Now, when we look at these situations and we're thinking about when can we take a derivative, it helps to visualize when we can't. So places where a function can fail to be differentiable. If we have a sharp corner here, we can't draw a tangent line there because we're not sure what kind of a slope is actually occurring there. What's really happening here is that our difference quotients are not equal to each other as they converge upon that sharp corner. We have a slope of -1 and a slope of +1. -1 on the left and +1 on the right. And so when we reach 0, we have two distinctly different slope values. So sharp corners do not become differentiable. A derivative does not exist at the corner. If we have discontinuities, we just talked about that. We can't draw tangent lines at the point of discontinuity because we're not sure where or how to indicate what's happening there with a behavior line. And finally, a vertical tangent. If we were to draw a tangent line, it would go straight up and down, but to describe the slope of a vertical line, that would be an infinite rise over no run. And that's an undefined situation. So the limit of our difference quotient there, when we have a vertical tangent line, we simply say does not exist. Let's look at a couple of examples. Here we have a piecewise function. The function is x squared minus 6x for values of x less than or equal to 3, and negative x squared plus 6x for values of x greater than 3. So to find whether or not f is differentiable at x equals 3, we'd want to look at first whether or not the function is even continuous at x equals 3. If the function is continuous, then we can look at whether our derivatives from the left and right are equal to each other. So step 1 here is the function continuous? And then we have to go back to our definition of continuity is the limit as x approaches 3 from the left of f of x equal to the limit as x approaches 3 from the right of f of x, and is my limit as x approaches 3, if that's true, is my limit of f of x equal to the function value at 3. So let's look at the limit first as x approaches 3 from the left. Well, as x approaches 3 from the left, we follow the rule x squared minus 6x. And because x squared minus 6x is a continuous function, we can see what's happening as we get closer and closer to 3 by plugging 3 into the equation. So we would have 3 squared minus 6 times 3, which would be 9 minus 18, or negative 9. Now, as we approach 3 from the right, we would use our second equation here for values of x greater than 3, so 3.01, 3.001, etc. And there, if we plug 3 into the expression, we would get negative 3 squared plus 6 times 3, which would be negative 9 plus 18, which would be positive 9. Well, negative 9 and positive 9 are not equal to each other, so our function is not continuous, which automatically tells me that my graph is not differentiable. We have a discontinuity at x equals 3. Let's look at another situation where we might be given a graph. Here we have a graph with lots of interesting things going on, and we want to find the numbers at which f is not differentiable and explain our reasoning. Well, here, as we move from left to right, let's take a look at some of these situations. Here at negative 4, something interesting is going on. We've got a sharp turn or corner, and as we know, that's one of the possibilities to prevent us from taking a derivative. So at x equals negative 4, we would say the graph is not differentiable, and our reasoning would be that there is a sharp corner. The left hand and right hand derivatives are not equal as x approaches negative 4. We have a sharply positive slope and a sharply negative slope, which do not converge. Our next situation where something interesting is happening is here at x equals 0. We can see that the graph jumps from a negative number to a positive number, and that means we have a discontinuity. So at x equals 0, we don't have a derivative because the graph is not continuous at x equals 0. Finally, if we look a little further down, at x equals 2, the graph appears to be going straight down, which means we have a vertical tangent line. Vertical tangent lines are also places where the derivative does not exist. So at x equals 2, there's a vertical tangent line, and therefore our graph is not differentiable at x equals 2. Okay, so those are our examples. If we go back to look at our topic, differentiability and continuity, differentiability implies continuity. If a function is differentiable, we know it's continuous. Okay, but just because a graph is continuous doesn't mean that a derivative exists at all points. We have several instances of where a derivative might exist or might not: sharp corners, vertical tangent lines, and discontinuities. And that's the end of our lesson.